So I've been thinking about what sort of blockchain videos I could do, and I decided to just look for blockchain on YouTube, right, to see what's already there. And I found a bunch of videos which they do explain how blockchain works, and I mean they're not wrong or anything, but I have a feeling like they don't explain it in the best way. They start from the bottom up. They really focus on this idea of block. I mean, it's in the name, right? Blockchain, so a block must be important. Whereas I think it's kind of a detail. In a sense, the block is just a part of the data model. So I thought I'd make a video trying to give a more high-level overview of how actually a blockchain works in 2025. I view a blockchain as just a new model of computing, okay? So what is then the old model of computing? It makes sense to start from that. So you have a user, all right? And the user wants to do some computation, right? So they interact with a computer, right? And this, well, this could be their local computer, or they could be using their local computer to talk to a server, okay, that's somewhere in the network. This works fine, okay, and it's how computation has been done since the beginning of computation. There is one assumption being made here, and that is that the user is trusting whatever this their local computer or the one on the network, right? Whatever the result of their computation is, they are trusting that. And this is fine, right? If you have an application like, say, a web shop, you're trusting your credit card details with the website, but because the website belongs to the business and you trust the business anyways because you chose to buy something from there, it's fine, right? You're not really changing your trust assumptions for that specific application. So how does blockchain work instead? Let's identify, okay, the user with their local computing device. Now this computing device connects to a network of computers. It's a peer-to-peer network, okay? So like torrents, if you ever used BitTorrent, or maybe if you're into that engineering, Kafka, okay? Kafka can be configured to run a consensus among multiple nodes. And all these are in communication among them, okay? So the user interacts with this network and submits some computation, okay, to this network. What's the difference? Well, the point is it's made in such a way that the user doesn't need to trust any single one of these computers, but just the rules that define the network, okay? So this means that there will be certain type of applications, for example, financial transactions, for which this will be a particularly well-suited architecture, right? Because if user A wants to send some assets to user B, okay, instead of deciding that we will trust some central server to keep record of this transfer, we decide that we will use a blockchain network to keep track of this transfer, and then neither of us will need to trust a central authority, right? But we will just trust the network and how it has been built, and also how the particular state of the network. So of course, in here we start getting into the details of how these things work, but of course, the network can still cheat on you. Okay, if there's like two computers, for example, then both operated by the same person, that won't work. So how does the network actually work, and how does it manage to provide these security guarantees? Let's think of it this way. There are four big components in how a blockchain works. The first is an execution layer. Okay, we'll call this execution layer. The second, let's choose some other color. This is the consensus layer. Then we have the data availability layer. And these, let's say, from a technological point of view, these are enough to make the blockchain work. But a blockchain is not just a technological system, it is also a social system. So you need a further thing, a further component, which is the, let's call it token engineering layer, okay? Or crypto economics, if you prefer. Something that overlaps between the technology and the social aspect of it. A blockchain to work needs these four components. So let's start with these three. Okay, these basically together, these replicate a a state machine. Okay, if you study computer science, it's one of the basic concepts. Okay, it's that of a state machine. Okay, that's an idealization of the concept of computer. A state machine, you can think of it as something that can be in a state. Okay, you can think of them as nodes in a graph, and then based on user input can move from one state to the other. Okay, and there are, of course, in modern computers, a very high number of states. Okay, because every time you move the mouse, and technically speaking, that's a different state on your computer. So you're moving in this graph to another state. This replicates that, but in a decentralized way now, because this under the hood is being run by a peer-to-peer network, right? As we saw, not by one computer, but by a peer-to-peer network. So the execution layer is, and by the way, these are called layers, but I don't really think that's a great terminology, because they're not necessarily stacked. Like, it's more kind of a modular architecture from how I see it. The execution, but I'll keep using this terminology, okay, because that's what's commonly used. The execution layer, it's responsible for taking user input and advancing the state, so computing how the state will change based on this input. And this is being run by every node individually, okay? So every single node in the network individually is accepting user input. I don't have a space here. I guess I'll make a small user here. Okay, the user is sending the input to the execution layer. Okay, all the nodes are executing the input given by the user. And then what they do after they each individually executed this state change is they reach consensus. And there's a myriad, okay, of consensus algorithms. What is a consensus algorithm? A consensus algorithm allows the network to reach an agreement, okay? Either via voting, or, for example, that's how BFT algorithms works, okay? All the nodes communicate and they kind of vote on what they think is the input they read, what they think is the correct state, okay? The correct final state. And then a final decision is reached, okay? And that state becomes final. Once that state is final, it is committed to the data availability layer. This means that a blockchain needs a place to store all of its data, okay? All the past data where we all reached the agreement, okay, this was final, okay? We put it here in the data availability layer. And that is what constitutes the ledger, okay? If you're thinking of the application of financial transactions, okay, which is the main application of blockchain. All this ledger of transactions, okay, will be stored in the data availability layer. Here there is a missing arrow actually then, because the execution layer is not just taking the user input, but it's also taking the past state, right? If you think of it as a discrete time, at time t+1, it's taking the new user input and the state at time t, right? And that comes from the data availability layer. So these three things together, they make the blockchain engine, okay? But now we are missing out, okay, and this important guy here that I drew out. Why? Why is this important? Because you have to think, this is not a permissioned network, okay? What would be a permissioned network would be the example of Kafka, right? I mentioned before. You are running some application that needs some that has different nodes, okay, and it's distributed, and it has maybe a consensus. But you, in the case of Kafka, you're whitelisting, okay, which nodes participate in that. You're not allowing just anyone to come in and join. Whereas here, most blockchains, okay, because by the way, also there you can, the situation is more nuanced. But on a basic level, okay, all blockchains are permissionless, which means anyone can participate in this peer-to-peer network. But then how do you manage? Well, first of all, why would people do it, right? Why? Because it's obviously it's expensive to participate in this network, to process the transactions, to store the data in the availability layer, to make all the network calls that are required for the consensus. All this is expensive. Why would you do it? Well, because there is a system, an economic system that incentivizes nodes to participate, right? And that's the token engineering part. And this, again, strictly from a strictly technological point of view, this is not required, right? But in order to actually have a network effect, Okay, in order to actually onboard new users onto, you need to have some token engineering. Okay, you either have a permission network, say for example that some government does now, they're talking about this, right? CDBC. Those would probably be permission networks, right? Then you don't need a token engineering system, because then you're just, you decide as the government, we're going to run this blockchain, we're going to create this blockchain, we are going to pay for all the nodes and the users. And then in some sense, it's more akin to a traditional, it's more akin to a traditional computing model, right? What I showed at the beginning. You're not trusting a single computer, you're trusting a network, but they're all operated by the same entity, right? Whereas here in blockchain, you're trusting a network where ideally each node is operated by someone different. How do you achieve that? Because you give incentives to people to participate and to act honestly. And that's basically the high level picture of how a blockchain works. Of course, it's a very high level overview of the thing. I could go into more detail on every single block. There's a lot of details. But yeah, I think this is a more useful picture to keep in mind. So to summarize, a blockchain is a distributed state machine that is also permissionless, and where there are incentives in order to keep the nodes, in order to incentivize people participating and to keep them honest. I hope that helps. Let me know what you would like me to go deeper in.